Homework 7a. Question number 1. The standard Gibbs energy of formation of ammonia is negative 16.5 kJ per mole at 298 Kelvin. What is the reaction Gibbs energy when the partial pressure of nitrogen, hydrogen, ammonia are all given? What is the spontaneous direction of this reaction? So the reaction of formation of ammonia refers to this reaction. So half of nitrogen 3/2 forms 1 mole of ammonia. And for this reaction, the delta G is called the formation, standard enthalpy of formation. And the energy is negative 16.45 kilojoule. Note that this is a standard state. The question is, if nitrogen, hydrogen, ammonia have partial pressure 314, what is the reaction and Gibbs energy for this reaction? So the reaction Gibbs energy at any instant for a chemical reaction is calculated by the standard state reaction Gibbs energy plus RT ln Q. The standard state reaction Gibbs energy is given, and the Q should be calculated by the product divided by reactants. So product here is 1 mole, and the reactants half and 3/2 for hydrogen. Okay, so plug in all the data, and Q is 2.31. Plug in this equation, delta G can be calculated. So again, pay attention to the unit. So kilojoule, and this one is joule. You need to times 10 to the minus 3, and that gives you negative 14.38 kilojoule per mole. Now, because the reaction Gibbs energy for this mixture is negative number, less than 0, and that indicates the forward reaction is spontaneous. Question number 2. The standard Gibbs energy of formation of the following reaction are given. Calcium carbonate forms calcium oxide and carbon dioxide, and their standard Gibbs energy of formation. It asks you to calculate the equilibrium constant at 298 Kelvin. So equilibrium constant and standard reaction Gibbs energy are related by this equation. And first you need to calculate the standard Gibbs energy of reaction, which is the formation Gibbs energy of product minus reactants. So plug in the data, we get 130.31 kilojoule, and then plug into this equation. So ln K is delta G divided by RT, negative. So delta G, you times 10 to the third power to become joule, all right, divided by RT, give you ln K, and K is 1.44 times 10 to the minus 23, and that's a very small number. Means the reaction does not favor product at room temperature. So at room temperature, calcium carbonate is a stable compound that does not form the product. Now the next question is, when temperature increases to 1173 Kelvin, so at high temperature, what will be the equilibrium constant? Now it gives you the standard reaction Gibbs energy at this temperature. So delta G at 1173 Kelvin is given, is 0.178. Okay. So it gives you this number, it asks you the equilibrium constant at 1173 Kelvin. Now in class, we derived the Van Hoff equation, allow you to calculate the equilibrium constant at a different temperature. And that equation is when you do not have the standard reaction Gibbs energy at different temperature than room temperature. So if you don't have this one, you have to use Van Hoff equation. But if you have this reaction Gibbs energy at 1173 Kelvin, then you just have use this equation again. So in this equation, delta G is at 1173 Kelvin, and the temperature is 1173 Kelvin. Equilibrium constant, it can be calculated at 1173 Kelvin. And so use this equation again, which is shown in the next slide. To calculate K at 1173, we use this equation again. Reaction standard Gibbs energy equals negative RT ln K. So ln K is negative delta G, all right, divided by RT. And so K should be e to the negative delta G over RT. Okay, so plugging all the data, all right, we'll get 0.982, so about 0.98. So you see, at room temperature, equilibrium constant is around 10 to the negative 23. When you increase to 1100 Kelvin, the equilibrium constant increase to about 1. So that's 23 orders of magnitude increase. All right. Question number 3. For a gas phase reaction, it was found that when 2 moles of A, 1 moles B, 3 moles D were mixed and allowed to come to equilibrium, the resulting mixture contained 0.79 C in the total pressure 1 bar. It asks you to calculate the mole fraction, the Kx, and the standard Gibbs energy of reaction. Now this reaction involves the moles before equilibrium, after equilibrium. And the best approach for this type of reaction is to list a table and show what is the initial amount before equilibrium and what is the whole the amount of every substance after equilibrium. Okay, so what do we know? Initially, you have 2 moles A, 1 moles B, 0 C, 3 moles D, and the total is 6. It also tells you at equilibrium, 0.7 C is formed. But at the beginning, you have no C. And therefore, that's the change of C. That's how much C is changed. And due to the stoichiometry, we know that D must be twice of it. So D is 0.79 times 2. And B is the same because the ratio is 1:1 ratio. A is also 1, so negative 0.79. It consumed consumed 0.79. Therefore, at equilibrium, then initial for A is 2 minus the change. So 2 minus 0.79 give you 1.21. For B, 1 minus 0.79 give you 0.21. And for C, it's the 0.79. For D, is 3 plus 1.58. And that gives you 4.58. And at equilibrium, the total amount, you add them together, is 6.79. From there, you can calculate the mole fraction. For A is the moles at equilibrium, so 1.21 divided by the total amount is 6.79. All right, and that gives you 0.1782. Now, similarly, for B, you use 0.21 divided by 6.79. That gives you 0.031. And for C, you use 0.79 divided by total amount, give you 0.1163. All right, similarly, you get D, mole fraction. Okay, so with this mole fraction, you can calculate the Kx by the product divided by reactants. So the product D, you should square it because the coefficient is 2. So the mole fraction Kxd squared times the xc divided by xa xd. All right, so that gives you 9.6. So this is a Kx. In order to calculate the delta G, we need to know Kp. And Kp, Kx are related by this equation. Kp is Kx times P to the delta V power. Delta V is the product minus reactants. So it's 1C, 2D added together is 3. And the reactants is 1 plus 1 is 2. So 3 minus 2 is 1. So delta V in this reaction is 1. And therefore, Kp is just Kx times P. And in this question, P is 1 bar. So Kx is just Kp. So Kp is 9.6. And now we can calculate delta G. Delta G is negative RT ln K. And we know K, so we can calculate delta G, which is negative 5.6 kilojoule per mole. All right, so for the last question, we calculate delta G first, using the formation Gibbs energy, calculate delta G, and then we can calculate the K constant. In this question, we do experiment, find the equilibrium concentration, then we can calculate the K. And from K, then we can calculate the standard state Gibbs energy change.